Picture handing one enormous job to a single worker. Read 100 research papers, write the whole review, build the tables, format the document. They start strong, but somewhere in hour 8 they have forgotten what page 2 said and small mistakes have quietly piled up. Now picture the opposite. A project lead splits that same job into pieces, hands each one to a specialist, lets them all work at the same time, and stitches the results back together. That second picture is the whole idea behind Kimi K2.6, an open model from Moonshot AI released in April of 2026. Its headline trick is something Moonshot calls an agent swarm, scaling to around 300 subagents across roughly 4,000 coordinated steps in a single run. But the model is just the example. The real subject is how a swarm of AI agents divides a giant task, works in parallel, and stays coordinated without losing the thread. Let us see how that works. So what is Kimi K2.6? It is an open-weight agentic flagship language model built for long-horizon coding and for running many agents on its own. Open-weight means something specific. Anyone can download the model's actual weights, all roughly 600 gigabytes of them, under what Moonshot calls a modified MIT license. In plain terms, it behaves like a normal permissive license. Free, commercial use allowed, no royalties. There is one catch, and it only bites at huge scale. If your deployment crosses about 100 million monthly active users, or $20 million a month in revenue, you must show the words Kimi K2 in your interface. Most teams sit well below both lines, so for nearly everyone it is simply free and open. It is also natively multimodal, meaning text, images, and video were built into one architecture rather than bolted on, with a vision component that can even pack several video frames together as one block. But an honest asterisk. At launch, image and video support was uneven across the places you can reach it. The official platform began exposing image input, while some endpoints like the coding command line tool kept vision internal and video stayed experimental. So whichever host you use, check its current capabilities before planning to send it pictures. A quick look under the hood, then we move on because the architecture is not the story. Kimi K2.6 is a mixture of experts model. It has about 1 trillion parameters in total, but for any single token, it wakes up only around 32 billion of them. Picture a wall of 384 specialist experts. For each word, a router lights up just a handful, and the rest of the trillion stays dark. It uses a memory-efficient attention design called multi-head latent attention, which keeps the model's running memory small. That detail matters more than it sounds, because a small memory footprint is exactly what makes long contexts and many simultaneous agents affordable to run. Its context window, the amount it can hold at once, is 256,000 tokens. Notice that number did not grow from the previous version. The improvement here is stability at that length, holding quality as the window fills up, rather than a bigger window. So remember, this is the enabler, not the plot. So why does this matter? Start with the felt problem. When one AI agent tackles a huge job alone, it works as one long chain of steps. Do step 1, then step 2, then step 3, on and on. And the longer that chain gets, the more it tends to forget early details and let tiny errors compound. Early autonomous agents stumbled badly here. They would lose the thread halfway through a long task. They have been getting steadily better, but reliability over very long jobs is still a genuine frontier. Now the timeless move, the one humans use for anything too big for one person. A project lead does not do it all themselves. They split the work into clear briefs, hand them to specialists, let everyone work at once and combine the results. That shift from one long chain into many short parallel lanes is the heart of everything that follows. And the second reason this model matters. Independent evaluators, the analysts who test these models without a stake in selling them, call it the new leading open-weight model. Not the smartest on Earth, and it is not, but the strongest one you can freely download and run yourself at a fraction of the closed Frontier's price. Open, cheap, and long-horizon coordination in one package. So what can a swarm like this actually do? Moonshot reports autonomous runs that chain together more than 4,000 tool calls and keep going for over 12 hours, with a budget of around 300 subagents in a single run. Treat those as vendor demonstrations, since the full logs are not public, but the shape of the DMOS teaches the idea well. In one, the system took a single uploaded resume, spawned about 100 subagents to match it against 100 different job roles, and returned 100 tailored versions. In a coding run on a financial engine, it reportedly worked for around 13 hours, tried a dozen optimization strategies, changed over 4,000 lines of code, and boosted the system's throughput by about 185%, nearly tripling it. The clearest one to picture, though, is a research review. One prompt to produce a long literature survey. Hold that example in your head, because it is exactly how we are going to open up the mechanism. Here is that research review, and here is where the real engine starts. Everything from now is the framework formally described in Moonshot's earlier K2.5 technical report, the version that K2.6 then scales up. So picture the prompt. Write me a full literature review. One coordinator, the orchestrator, the project lead, looks at the goal and breaks it into different kinds of subproblems. Search for sources, pull out citations, group the topics, draft an outline. Write each section, build the tables. Crucially, these pieces are not identical copies. They are heterogeneous specialists matched to the job by skill, a searcher versus a reader versus a writer. So the system is built from one trainable orchestrator and a set of frozen subagents. The orchestrator is the part that genuinely learns, the lead getting better at leading. The subagents are fixed copies made from set checkpoints of the model, specialists who do not change mid-project. And the orchestrator conjures them dynamically, deciding how many and what each does for the task in front of it, rather than picking from a fixed menu, then running them in parallel. This is the classic orchestrator-and-worker pattern. One task forks into many specialist lanes that light up together. Now the single most important mechanism, the one that makes coordination across thousands of steps even possible. It is called context sharding as opposed to context truncation. Here is the problem it solves. The orchestrator has a limited window. If every subagent dumped its entire transcript, every dead end and raw result back into that window, it would overflow almost immediately. The old, reactive way to cope was to truncate. Just compress or throw away old history when you run out of room, which means losing the thread. This framework does the opposite proactively. Each subagent keeps its own private working memory for its slice. All the heavy scratch work stays out at the worker, and only the task-relevant outputs, the distilled results, get routed back to the orchestrator. So the lead's window holds the coordination state and the clean answers, never everyone's mess. Picture each worker holding a dim cloud of private memory, with only a small glowing result traveling inward. That selective return is how the swarm stays coordinated when one agent alone would have drowned. If you split work across many parallel workers, how do you even measure how long it takes? The framework measures cost in what it calls critical steps. The intuition is the critical path. For each stage of the job, the time is the orchestrator's own steps plus the maximum of the parallel worker's steps, not the sum. In other words, a parallel stage takes as long as its slowest worker, while the faster ones finish early and wait. This choice is subtle but smart, because measuring cost as the slowest branch directly rewards cutting delay, getting answers back quickly, rather than spawning agents for their own sake. The reported payoff is striking. Compared to a single agent doing the same work, the swarm cut response time by up to 4.5 times, while improving accuracy, raising a quality score from about 73% to 79%. faster and more accurate at once, the rare result where both arrows point the good way. Two more pieces complete the mechanism. First, what happens when a worker gets stuck? Moonshot's documentation says the system detects when an agent stalls or fails and automatically reassigns or regenerates that subtask, so one stuck worker does not kill a 12-hour run. Be precise, though. That is a vendor claim. The underlying paper does not describe the detection algorithm, so analysts note the recovery logic is opaque and cannot be tuned. Trust the behavior, not a documented mechanism. Second, the deep part, how the system was trained to coordinate. The method is called parallel agent reinforcement learning. Only the orchestrator is trained. The workers stay frozen, kept out of the optimization, which gives clean credit assignment and training stability, the paper's two stated goals. The reward has three parts that fight two opposite mistakes. One part pushes it to actually spawn workers, so it does not lazily collapse back into one serial agent. Another rewards workers that finish useful work, so it does not spawn junk. The third is just the final task outcome. The two helper rewards fade away over training, leaving pure results to take over. So the lesson the model learns is not how to work. It is how to coordinate. And that is the real point, that coordination became something you can train. So what did this version itself contribute? Mostly scale and stability, not a brand new mechanism, and being clear about that keeps the story honest. It takes the earlier framework and grows it roughly 3 times wider, from around 100 subagents to around 300, and deeper, from roughly 1,500 coordinated steps to around 4,000, while targeting the quality drop that long coding runs used to show as their context filled up. There is one nuance worth holding onto because it stops the headline from being misread. That 4,000 is a swarm-wide budget, the total shared across all the agents, not 4,000 steps each. With 300 agents, that works out to only about 13 steps per agent on average. So the picture is wide and shallow. Many quick specialists, each doing a small focused job, coordinated together, not 300 deep independent marathons. Breadth coordinated is the move, not depth piled onto every worker. So where does it rank and what does it cost? Here is the honest version, more useful than the hype. On one independent intelligence index it lands around 4th overall, behind the closed leaders from Anthropic, Google, and OpenAI, and on pure single-turn reasoning, the hardest questions answered without tools, it trails the very top. But on the agentic dimensions, the actual coordination and tool use, the leap is real and independently seen. Its agentic skill rating jumped sharply between versions, and its tendency to make things up roughly halved. On coding, it sits about level with the latest leading models on agentic benchmarks, just under the strongest Claude effort on some runs. So it is genuinely in the frontier conversation, while leading the open field outright. And here is the practical headline. Cost. It is several times cheaper than the closed frontier, with input priced under $1 per million tokens versus around $5 for the closed leaders, roughly 5 times cheaper for comparable work. You can reach it through the official app and interface, download the raw weights, or use a long list of cloud hosts, with no single vendor lock-in. All these scores and prices shift constantly, so hold any single number lightly. Let us be honest about where this strains, because a swarm is not a free win. First, open weights do not mean it runs on your laptop. Full quality needs roughly 8 high-end data center accelerators, a compressed version about 4, and on consumer hardware it crawls at a handful of tokens per second, which is impractical. Open means auditable and self-hostable by those with serious hardware, not free on a laptop. Second, coordination has real overhead. Spinning up hundreds of subagents is pure waste for a small task one agent could finish in minutes. The payoff only shows on genuinely large, splittable jobs. Third, there are named, documented failure modes. State drift, where one agent changes something and another keeps working off a stale snapshot, so their views of shared reality quietly diverge. And the coordinator bottleneck, where if every piece funnels through the orchestrator, the so-called parallel work serializes and the speed-up collapses, and the deepest limit is shared by the whole field. Over very long horizons, small errors can still compound across thousands of steps. Context sharding and swarms push that wall much farther out than a lone agent could reach, but they do not abolish it. A frontier being pushed, not a problem solved. Before we close, 3 quick corrections because each is a trap people fall into. First myth: an agent swarm is just 300 copies of the same bot brute forcing an answer. No. They are heterogeneous specialists, a searcher, a reader, a coder, a formatter, matched by skill, working a shared and mostly shallow step budget. Coordinated division of labor, not brute force. Second myth: this is the new smartest AI that beats everyone at everything. No. Independently, it ranks around 4th overall, the leading open model, strong on coding and agents but behind the closed leaders on pure reasoning. The story is open, cheap, and long-horizon coordination, not number 1 intelligence. Third, a sourcing trap worth naming. The swarm and training mechanism is not from this version's own paper. The headline runs are also mostly vendor demonstrations without public logs, so say Moonshot reports this, never it reliably does this. The deepest mechanism comes from the earlier K2.6 technical report, which this version simply scales up. So step back, and here is the payload. For years, the main way forward was to make one model bigger and smarter. Kimi K2.6 is a clear sign of a second path, just as important. Make a model better at orchestrating many cheaper workers. And the deepest idea is that coordination itself turned out to be a skill you can train. The method shows you can reinforcement, learn the lead, freeze the team, and reward good splitting. So dividing and reuniting work becomes a learned, first-class ability rather than a hand-coded script. Shipped open and cheap, that capability is not locked inside one lab. It is worth noting plainly and neutrally that Moonshot is a Chinese lab, and this launch arrived amid broad scrutiny of where advanced AI comes from. But that is context, not the lesson. Here is the whole thing in one line. One agent grinding alone hits a wall. A well-coordinated swarm split the work, keep each worker's memory separate, send back only what matters, then rejoin, pushes that wall much farther out. The version number will date. The move, fork, parallelize, coordinate, rejoin is simply how hard problems get solved.